Hello everyone, and today we'll be seeing one of the very good problem from Geeks for Geeks. It says k closest values. It is a very good problem, and by that I mean it's a good in terms of understanding implementation and an aggregate of multiple data structure. So I want you to have a good attention while we are going through this code, the problem statement. We are given, okay, I'll quickly explain that we are given a root of a binary search tree, a target value, and an integer k. Our task is to find k values within the binary search tree which are closest to our target. So we will have a return k values. So in this case, for with an example taken, k is 3, so 3 values which are closest to target, and our target is 17. So you see, with 17, these three values are very closest. You take 4, it's very farther. You take 22, it's way farther on the right hand side. Let's again go to the problem statement. The closest value is taken by choosing the one that gives minimum absolute difference from the target. Yeah, correct. And note, in case of two values have same absolute difference from target, choose the smaller one. The target may or may not be present in the BST. Okay, you can return the values in any order. To the driver code will print the sorted order only. That's nice. So in this case we are provided with a binary search tree and our target is 17, with an expectation that we will have 3 nodes which would be very closest to the target. So we started off from 17, which checked 28, 22, 4, 12, 10, and 14. And based on that, we have populated this. Let's not go into the approach how we are going to do it right now. I want you to get submerged into the problem statement. So why they have choose 14 is because absolute difference between 17 and 14, 20 and 20 is 3 and 3. Okay, 14 and 20, the difference is 3. And for 12, the difference is 5, I guess. So these 3 nodes they have chosen 20, 12, and 14. In the similar way, when the target is 5 with this binary search tree with k is equal to 2, we have 2 values, and absolutely 5 is actually present within the binary search tree, so difference is 0. That means 5 is there. And the second number which is closest to 5 is 4, not 8, not 1, but 4. Yeah, so that is why 4 is over here. Makes sense. So the objective is clear to us, that we need to get k elements must be closest to target. So these are the objective. Now with this objective into picture, what we will try to do is, so we can have with one approach number 0, we can have something like from the BST convert it into an array and post that process for the closest. You see, finding closest is not a big deal when it comes to an array. It's a simple linear process. It obviously will come into a window. So in this case, a window was 20, 12, 14. You see 12, 14, 20, it lies in one fashion. So if I take this an array, if I take this a BST within an array, you see it would be, give me a minute, I would just jot it down, 4, 8, 10, 12, 14, 20, 22. And you see 14 would somewhere line over here, not 14, whatever target was 17, right, if I'm not wrong. Yeah, So the 17 would lie somewhere here, and we take two pointer, one over here, one over here, and we get a consecutive elements, which is 12, 14 and 20. You try it every time. I'm not like limiting you, but you try every time and you'll get a closest pair or closest k elements in a consecutive fashion, and which is logical itself. So it's not a big deal to find within an array, but we are lacking on one very big thing, that is space complexity. So space complexity over here would take O of n. That's okay in some aspects when you have n is slightly lesser than k, but in a case where n is sorry n is slightly greater than k or equal to k, but n is way greater than k, then that's not a very efficient approach. You could have saved a lot of numbers in terms of space complexity. Again, we have not utilized the full potential of binary search tree, and here in this case we would use a binary search tree to its fullest. So earlier the bottleneck was converting a binary search tree into array so that the operations could be easier. Nice. So for easier operation and for a sorted array, we want to have an in order traversal. That's for sure correct. In order traversal, what it will give? A sorted list. So sorted array, let's say list or array in one and the same thing. So within the sorted array, this was our point of concern, and we know that result is always consecutive. Also we know that result is of size k. This is from the finding, and this is the ask from the problem. Cool. So why not we go ahead, do the in order traversal, and then keep track of these k elements, check for any updates. By updates I mean closer elements, if getting closer elements. So if you are getting closer elements, so keep updating your arrays such that it's closer and closer to the target, so that it is closer and closer to the target. And once it's done, if good, update the array, check for the next one, update the array, check for the next one. But if not good, then don't worry, go to the, if not good, go to the second one or do an optimization check. What optimization check, we can look at further. I would not complicate this more. I guess it's a good guess given. So you see, we wanted to have a data structure which would contain k elements for us and an in order traversal. In order, everyone knows that it's left to current to right. So let's segregate what we would do in all these cases. Left we would just iterate, current we would check for the above, and on the right we would iterate again. Check for the above, by check for the above I mean these steps, these checks we wanted. So far so good. So yeah, let's, so I'll have what do you say, a data structure. In my opinion, DQ sounds well because we wanted to add and remove the array, the elements from the data structure, and in a timely fashion. So integer q is equal to new linked list as a DQ, and I wanted to process this with the help of root target k. Okay, I'll also provide a q here. Nice, provided a q. And what I'm trying to do here is q would be populated here, and once the queue is populated, I will return a new array list with queue. Why array list? Because yeah, the question demands array list. I'm not sure why, but okay. So nice. Let's go ahead and let's implement this method. So this method, which would return nothing, that's void. It would take node, it would take DQ with integer, it would take integer target, and it would take integer k. So many parameters we are passing, but yeah, cool. Now the classic check for null. If root is equal to null, I would return from here. Beyond, we are doing an in order traversal, so left, current, right. So yeah, this is our left. I wanted to go to processing of left node with the same queue, with the same target and the same k. Again, we want current. We wanted to check what will happen, and I will also say right. Wait a second, I'll just do right first. It would be much more simpler, and we can jump to what processing we will do in the current. Yeah, cool. So now we are coming to processing. As we mentioned, keep track of these k elements. I wanted to keep track of these k elements, so what I'll do is q dot size. If it is lesser than k elements, I want k elements. I'm short of it, so I'll populate. So I'm short of k elements. I'll go ahead and I'll just populate these things, nothing much. So q dot offer root dot data. That's it. Because my k elements are not fulfilled. Else, what happens if my k elements are fulfilled? I wanted to check whether if my k elements are fulfilled. I wanted to check if I can take this root data or not. How can I check this? In other words, I wanted to check that is root data closer to target. Cool, that's the thing I wanted to check. You see, we are populating a queue, a DQ to be precise. So a DQ would be populated in a fashion like Q U E. So this for the spelling. So k element is, let's take I plus 1, I plus 2, and so on. I plus k minus 1. Anyways, up to so on. Now, you see, if I'm upon the root, I'm on the root, then I wanted to know to what node I am compatible enough. So I wanted to check whether this element is not feasible, this element is not feasible, this or the last one. Last is not feasible with the target. When I'm saying feasible, I am checking for the closestness. So with the root, shall I check last? Shall I check first? Shall I check second? Or what? So the answer comes out to be what data we are storing. So we are storing first element is the smallest, and the last is the largest. Why so? Because we are processing in an in-order traversal, right? So if you're offering the first node from the in-order traversal, it would be the smallest one. Now, if I'm on the route and my probability is getting into this, then I should be way ahead of I, or I should be, the root should be greater than last. That is for sure, because every element which can possibly enter would be a greater element from here. So if my chances are against the first node, that means I am not qualified enough to enter into the list. So I should ideally go ahead and check with the first node, because the difference from smallest to target would be much more greater than the last to target. You get the point. So if I'm having, consider with an example as a list of 1, 2, 3, 4, and I wanted to have a target as 5. Now, my conditioning with 5, should I check with 4 or should I check with 1? So the obvious answer is I should go ahead and check with 1, because smallest first, 1 difference 5 is much greater than last, which is 4 difference 5, which is a bit smaller. That's why what I'm trying to do here is I'll check mat.abs q dot get first minus target. That should be greater than mat.abs root.data minus target. So this means root data. So if this is true, then it means root data is closer. So consider this. So consider it. Else it means root data is far, which means root data is much greater. So does it make sense to go further on the right hand side when the root data is greater? Nah, it doesn't make sense. So I'll just go ahead and return right from here, because on the right hand side, when we go ahead of this else, we are processing the right side, and we don't want it to process right side because every node on the right hand side is greater, and if it is greater, it's of no use for us. We want smaller elements. So it's a match. Coming back to, it's a match when the root data is closer. It's a match. Feed it in our queue. So what I'll do is q dot poll la first, because as we've seen that first is no more use, and q dot offer last. Why last? Because I wanted to keep the integrity. I wanted to have a smallest element on the first and the largest element on the last. Offer last is root dot data. So far so good, and in this way we have traversed our our array without creating an external memory space, and we have populated a queue as well. Let's compile this one, whether we have made any compiler errors or not. I think we didn't made. Let's submit this one for checking our code with the rest of the test cases. And one sweet thing with this code is, oh, cool, nice, great. It has submitted. So I was saying a cool thing with this approach was that we are storing in this fashion where we are having first and last within the queue as smallest and largest respectively. So first would be always smallest and the last would be always largest. So it's a very good thing that we don't even want to sort it and we can directly return this. So anyways, the question didn't ask us for to do that, but yeah, we did a good work. So this was about it. It was a certainly very good question. And for more such BST related content, click the video on your right and I'll see you in the next one.